working with Professor Varun Bhalerao and Professor G.C. Kumar at IIT Bombay. And today I will be talking about how we do the GRB afterglow searches with this robotic telescope that we have automated named Growth India telescope. So starting with like what GRBs are, like there have been various models that have been proposed how they generate. Typically, like there is a central engine which is a progenitor of this particular GRB. In most of the cases, it is some compact object like black hole are created surrounded by this accretion disk coming from this progenitor. And then also these relativistic jets, which consist of these high Lorentz vector cells, and they produce this some sort of shock as within the jet itself, which gives rise to this gamma ray energy emission in which we call as GRBs. And as these jets move into this interstellar medium or some sort of wind medium, they interact and produce something called as afterglow, which shines all the way from all the way from high energy to the very low energy in radio. And all of this, so I won't be talking about what GRBs are producing, but I will be talking more focusing on the afterglow, because this is one of the things that is observable in the optical, and that's what we usually look after. So there is also an interesting stuff happening. So with the forward shock, sometimes there is also this phenomenon of reverse shock is seen, where that slows down into the medium, this produces this reverse shock, and that both of these type of shocks together produce a very nice interplay and cause a lot of variability into these GRB light curves in the optical. Mainly like this reverse shock dominate the light curve at very early time, and in a few cases it dominate even this forward shock emission, and later on like forward shock emission that has been seen in most of the cases. So if we look at the typical GRB light curve that we have, follow-up of all of these really show this very steep decay with following some power law index, and that's what has been typically observed. But very few GRB also show this reverse shock emission as a rise signature in the GRB afterglow. So that's what we usually target. The telescope that we use is this 0.7 meter telescope located at Hanley. This is a 70 centimeter telescope accompanied by this indoor camera, which provides a field of view of roughly the size, twice the size of roughly a full moon, and that's what makes this particular telescope suitable for the GRB follow-up, as it can like even tile the localization area of the GRB, which is typically posted by these high energy satellites, as well as it can also do this targeted follow-up like any other typical telescope that we have. The important thing is like the sensitivity of the telescope, where it can go up to 20.5 to 21 magnitudes within 5 minute exposure, and can also take these deep exposure by coating many images. The way we have designed and the triggering on this telescope is it's completely automated, where it looks for these alerts coming from these servers, and then it look into quite a bit of filtering part whether the particular event is suitable for follow-up with this telescope or not, and then eventually it triggers the telescope if all of these triggering criteria are followed. It notifies us by posting a few of these important parameters. It posts these. It gives the different phone calls to the observer so that everything can be followed up immediately, and give us some hint of where roughly in the sky this particular event has happened and what the light curve looks like. And it automatically triggers the telescope if again the event is very suitable, so that there's no wasting of time, because all of these GRB afterglow decay very rapidly within a day or so. And all the interesting physics that is happening over there is very early into this. So it's very important to catch these as early as possible, and that's what we have been trying to do over like past few years. Since the commissioning of the telescope, we have observed roughly 84 GRBs up to like December last year, and the typical time that we have obtained is 2 to 3 hours from the trigger, which is just like sharp peak over here, and also there is a bump over here, which is like within a day or so. This is like the typical time, but we have to account for the thing that the GRB trigger might come into the daytime, but the only way we can follow it up is in the night time. So we have to wait for that particular thing for the first visibility window when it is observable. So if we correct for that, then the number of GRBs that we follow within first hour or so shoots up more than 50%. And recently we have like implemented this automatic triggering, which has take it to more than 85 to somewhere around 85% of the GRBs are being followed up very rapidly within first hour or so. The fastest trigger that we have obtained so far is 39 seconds. Look at this number, which is like if you remember, there are these satellites where one of these is Swift, which has this automatically slewing to this telescope, taking over images to look for the afterglow, which again take roughly 100 seconds or so after the GRB trigger time, and we are surpassing that in a few of the events which are happening in the night time itself. looking more into like these GRB compilation of the afterglows, where we have roughly 30% of the GRB that we have followed up shows these detection in the optical bands, various optical bands. So I have plotted over here is like the GIT data plus all the available public data for the GRBs, and these show like all of these different kind of red curves showing typically a power law, plus there are few which also show this rise or like flattening at very early time. So the main thing to look out from this plot is that all of these GRBs that are marked are actually show some sort of rise in the very early time, and then they started decaying, because that's what is the signature of like the reverse shock in all of them. So roughly 60% of the GRB that we have followed up show this reverse shock kind of signature, although it's not fully like modeled yet. So most of the GRB probably require like a detailed modeling to ensure that it's actually due to the reverse shock, not due to the like the rising part of the forward shock itself. And that's what we have obtained so far, and we'll be like looking into more detail of all of these events, and I will try to publish this. So another important thing that I would like to emphasize that in terms of result, that the typical response time that we have is roughly from seconds to minutes, and that's what is like very important for all of these GRBs. With the help of these, we have been able to actually discover the afterglows in the optical itself, not just the detection. There have been a couple of these examples. One of those is such where we search for like Fermi localization of wide area of a few degrees, and found this nice afterglow which was decaying with the power law. Also for this recent GRB, we again discovered an afterglow, which is probably the first time an Indian telescope is doing discoveries of the afterglow instead of just detecting the GRBs. Also, we have like a few nice results where for this one particular GRB, we detected the most delayed flaring that has ever happened in a GRB. Like summarizing this, that roughly 60% of our GRBs show the signature of the reverse shock, which we again like look back to this number and we try to find more and more accurate rate. And the final point I would like to make is that like this automatic triggering is probably will be very important when we look more into detail of this reverse shock percentage, because currently we don't know how many of the GRB like are dominated by the forward shock or the reverse shock, because there hasn't been much of the data at very early time, and this telescope follow-up will probably shine some more light into like how many percent of the GRB actually show this kind of reverse shock emission, and how many just actually show this forward shock related emission related afterglow. So I will stop here and will take a few questions.
What is the rate at which a GRB is triggered usually by a X-ray monitor, and what is the rate your optical telescope can monitor?
So roughly like the GRB rates are 1 GRB per day from like typical high energy satellites. Most of these are from the Fermi, which has like very wide localization of a few tens of square degrees to 100 square degrees, which are essentially like hopeless to follow up with most of the optical telescope, because you will have to spend a couple of nights to like cover the whole localization. But we just trigger everything which are like this localization better than 1 square degree, so that we can just take a few images and don't waste a lot of telescope time. And this is roughly like a couple of GRB each month would be something which will trigger.
So this 60% is from the December 2022.
So this 60% is all from all of the afterglow that we have detected in our GIT data basically.
So how many GRBs are there total?
So with respect, so all of these GRBs, that 84 that we have shown, that goes roughly around 18% or so, 18 to 20%. But again, that is also Swift GRB. There are also Fermi GRBs which nobody is going to follow up, and nobody will be able to comment on whether there was any reverse shock or not, because we haven't detected any afterglow for those GRBs.
One more thing, the reverse shock signature are generally seen up to 100 to 500 seconds.
Yeah.
So you are detecting up to from 1 hour to 10 hours. So what is the probability?
Not for all of the GRBs. So most of these signature are like within 10 to the power 2 to 10 to the power 3 seconds. Like essentially within first hour or so we usually see these reverse shock emission. But if you also like along in a few other cases when the like ISM density is high, this reverse shock can like elongate a little bit, and can even be shown for like 10 to the power 4 seconds or so. So there have been cases, something like the one I showed in the last slide, which is this last one. This actually showed a reverse shock of 2 for 3 into 10 to the power 3 or something like that.
Thank you.